When engineers plan a massive infrastructure project, like a dam, they rely entirely on physical dimensions. Length, mass, and volume tell them exactly how much material to order and how long construction will take. Software engineering lacks all of these physical dimensions. Digital products have no weight, no volume, and no measurable length. Without a quantifiable size, project managers lack a foundational variable. Predicting total cost or resource requirements becomes a matter of guesswork rather than engineering. To plan a digital build, engineers have to create a mathematical proxy metric. They need a way to translate abstract digital concepts into hard, quantifiable data. The oldest and most foundational estimation technique used to assign a size value to software is measuring lines of code, or LOC. The premise of LOC relies on a very simple correlation. The more source code lines a system contains, the larger its estimated size. This method originated in the 1960s and 1970s. In the early days of software development, before the existence of advanced algorithmic models, engineers needed a reliable heuristic to plan their workloads. They observed that writing more code required more human typing. An increase in typing meant an increase in development effort, which drew up the ultimate financial cost and extended the timeline. By counting lines, early programmers took an unmeasurable digital concept and converted it into a concrete baseline variable necessary for formal project management. A standard LOC count does not evaluate every line of text within a file. It specifically targets executable source code. This diagram shows the counting process, stripping non-functional elements. A scanner parses the file, isolating logic statements. Blank lines and comments are excluded. Only lines providing direct machine instructions represent structural effort needing estimation. Different software organizations might employ slight variations in their exact counting standards, but the primary objective remains identical across the industry, isolating the functional logic. Calculating LOC is an act of filtration. It removes human notes and formatting choices to expose the pure mechanical effort required to build the software. Because modern software projects are massive, engineers use prefixes to scale the metric. KLOC, or kilolines of code, represents thousands of lines. For infrastructure projects, like the kernel of an operating system, they use MLOC, meaning millions of lines of code. These charts illustrate the difference in scale. A basic calculator program might total 400 lines of code, while an online banking system hits 80 KLOC. The banking system requires a massive influx of code to manage transaction databases, loan processing, ATM modules, and security protocols. Standardizing these scale units allows engineers to instantly categorize the magnitude of a project's complexity at a single glance. How do developers estimate the number of code lines before they actually write any code? They pull initial estimates from historical company data and rely on expert analysis of similar past projects. Predicting that initial size is the first step in a rigid mathematical sequence. The estimated size dictates the human effort required. The required effort subsequently dictates the total development time, and that time frame determines the ultimate financial cost and resource allocation. Advanced cost estimation algorithms, like the Kokomoko model, relied entirely on this sequential pipeline to function. The entire financial architecture of a software development cycle balances on the accuracy of that initial LOC estimate. LOC has a distinct paradox. Two separate software projects providing identical functionality can yield vastly different code counts. The primary distorting variable in LOC estimations is the choice of programming language. This comparison illustrates the distortion. A specific program written in C might require 120 lines of code. That same logic, written in Python, might only take 45 lines. Developer experience adds another layer of variance. A veteran programmer will often write concise code, while a beginner working on the same problem might write longer, bloated logic. Modern development frameworks and reusable libraries artificially deflate LOC counts by automating tasks that previously required manual coding. Because LOC is highly vulnerable to these external factors, using the metric without factoring in language or team experience will severely skew a project's budget. Consider a real-world scenario. An engineering firm reviews its data and predicts a new online shopping system will require 50K LOC, 8 developers, and exactly 9 months to deliver. They achieve this precision by comparing the new project strictly to historical data that shares the exact same programming language and team skill level. Standardizing these internal variables, comparing Python projects to Python projects, neutralizes the flaws of the LOC metric. LOC remains ubiquitous because its straightforward numerical output is exactly the format complex predictive algorithms need to generate cost and time estimates. LOC functions as a calibrated business tool, yielding accurate results only when internal variables are controlled. If LOC measures size, the logical question is whether volume equals quality. Does writing more lines of code result in better software? Judging developer performance purely by code volume incentivizes engineers to write unnecessarily long, unmaintainable programs. Mere volume tells you nothing about the health of the system. Actual software quality is measured by its strict correctness, its processing efficiency, and its maintainability. True engineering excellence is frequently demonstrated by achieving complex system functionality with the fewest lines of code possible. While lines of code accurately measures the physical act of typing instructions into a machine, the true size of software is ultimately defined by the complexity of the problem it solves.